this will be the chemistry quiz for Chemistry CA Week 6. Which of the following mixtures can be separated using filtration? So to what you can separate using filtration is an insoluble solid in a liquid. Oil and water are two liquids that you can separate it in filtration. Salt and water, salt dissolves in water, so you can't not filtration. Sand and water, sand is insoluble in water, so you can filter it out. And sand and iron fillings, it's both solids, but you can't filter it. That's the answer is sand and water. It is required to heat a beaker containing some alcohol. How should this be done safely? In class they said alcohol is highly flammable. So if you heat it using a Bunsen burner like you would in any other liquid, it might burn. But you need to heat it using an electric heater or you need to use an electric heater. That's what you say in the written part if they ask you. But you have to heat the water electrically, because a Bunsen burner or a flame can make it burn and be highly dangerous. Which of the following statements define sublimation? Sublimation, we took it before. It's basically when a solid changes directly to a gas without going into a liquid state, like dry ice. Which of the following are steps involved in the separation process to obtain dry sand and dry salt from a mixture of sand and salt? When you have two solids like this, first you begin using selective solubility. You put water to dissolve the salt and not the sand, and then you filter it, so you can filter the sand and leave out the salt in the filtrate. You put the sand in an electric oven so you can dry it, and the salt you can crystallize it. First we add excess water and stir to dissolve all the salt. Carry on filtration to separate the sand as a residue and on the filter paper, and dry sand in the electric oven. Carry on crystallization to obtain the dry salt from the filtrate. We can't add excess water and stir to dissolve the sand and the salt. Sand doesn't dissolve. And heat excessively the filtrate to obtain dry sand. No, we have salt in the filtrate, not sand. Sugar dissolves in water and alcohol, and salt dissolves in water but not alcohol. Which of the following are steps involved in the separation of a mixture of salt and sugar? They told you that salt doesn't dissolve in alcohol. But they basically gave us the answer. Also, again, selective solubility. We put excess alcohol so we can dissolve the salt. So we can dissolve the sugar and leave the salt. We then filter the salt out of the solution. In the filtrate we have sugar and alcohol, and in the residue we have salt. And then we put the residue in an electric heater to dry, and slowly in an electric heater we heat the filtrate, not over a Bunsen burner, because again it can burn. So we first add excess alcohol to the mixture and stir. Filter the mixture to separate the salt and allow the salt residue to dry. And heat the solution to crystallize the sugar using an electric heater. If we add excess water, both the alcohol and the sugar, both the salt and sugar will dissolve. And if we heat alcohol, heat the solution to crystallize the salt using a Bunsen burner. First of all, we won't crystallize the salt, would crystallize the sugar that dissolves in alcohol. Salt would just be a residue from filtration. For distillation is a technique to separate miscible liquids. What they mean with that is liquids that dissolve in each other, or maybe يعني homogeneous mixtures عامة, like salt and water or whatever. The basic apparatus when using distillation is you have a round bottomed flask here, and then a thermometer, and then you have a condenser here. I don't remember the exact thing, but you get the idea. And another round bottomed flask here. So here we have the original solution, and whatever we get here is the distillate, and the condenser is just the vapor comes into the middle of it and gets cooled by constant water moving in and out of the condenser. So what are the apparatus needed to perform distillation? Thermometer, condenser, Bunsen burner to heat the solution itself. And funnel and pipette you don't need it for distillation. The liquid collected at the end of distillation is called the distillate I just showed you. And whenever two liquids with boiling point that are close to each other are to be separated, we use fractional distillation. Simple distillation, like the one that I just did, is for liquids or solutions with components of different there is a big difference between their boiling points, but if it's close boiling points, you use fractional distillation. And fractional distillation is a long tube that has obstacles, and it's only cooled by air. You don't need water like in it like you need in simple distillation. You only use the air when it's being cooled. A beaker containing an ethanol solution should never be heated using a Bunsen burner. I said this before, but I say it again. If you heat ethanol or alcohol using a Bunsen burner, it will burst into flames because alcohol is highly flammable. Which of the following techniques is used to separate black ink into components? So, to separate black ink into components, we don't use distillation like the first picture, or filtration, or fractional distillation. We use paper chromatography. You see here the black ink is the little dot. The black ink is the little dot at the bottom here, and it separates into all of its components while going up. Copper sulfate can be separated from its solution by crystallization. Copper sulfate is most of the time crystals. You use crystallization to separate it. Sodium reacts vigorously with chlorine gas to produce sodium chloride as shown in the following chemical equation. In an experiment, 14.2 grams of chlorine reacted completely with a given sample of sodium. Given atomic masses, Na is 23 and Cl is 35.5. Sodium reacts vigorously with chlorine gas to produce sodium chloride as shown in the following chemical equation. In an experiment, 14.2 grams of chlorine reacted completely with a given sample of sodium. Given atomic masses Na is 23 and Cl is 35.5. First we check if the equation is balanced. احنا in the reactant we have 2 Na atoms, and we also in the reactant we have 2 Na and 2 Na. In the reactants we have 2 Cl, and also in the products we have 2 Cl. But the equation is balanced. First, find the number of moles of chlorine reacted. So to find the number of moles, it's N, the number of moles, equal M mass over M capital M molar mass. فإحنا we have N, the mass they gave us to us 14.2 grams of chlorine, 14.2 over the molar mass. For the molar mass here they said chlorine gas. Gases are mostly diatomic, so we have 2 atoms of chlorine instead of 1. So 235.5, 14.2 over 71, and then I just put it in my calculator. 14.2 divided by 71, and you get 0.2. Now they told us they wanted 3 significant figures, but we add 2 zeros to make 3 significant figures. Find the number of moles of sodium chloride produced. For now we use RRGR. We have the number of moles of chlorine, but we can say Cl2 produces 2 NaCl. This is so we're doing RRGR. RR is reactant ratio and GR is given ratio. For the GR, they gave us that chlorine is 0.2 moles that we found in the last question, and for NaCl we don't know it, we put X. For Cl2, for the RR we have 1 mole and 2 moles of NaCl. You multiply. Also RR and GR they have to be in the same unit for Cl2, but I use moles here. So 0.2 times 2 equals 1x. 0.2 times 2 is 0.4 equals x, and again they want 3 significant figures, but you add 2 zeros to make it 3. And then for the last part, find the mass of sodium chloride produced. فاحنا here we got the amount of moles of sodium chloride. From this equation we can rearrange it and get that mass is moles times molar mass, and we got the moles as 0.4 times molar mass of sodium chloride. Sodium chloride, as we got from the reaction, is NaCl. To find the molar mass, you add the atomic number of the atoms. Na is 23 and Cl is 35.5. You get 58.5. And 0.4 times 58.5, you put it on the calculator, you get 23.4, and it's already to 3 significant figures. here they want us to balance an equation. احنا first they told us liquid hydrogen peroxide H2O2 liquid decomposes into water H2O. Water, they said water, it's liquid as well, and oxygen gas O2 gas. فاحنا we have H2O2 decomposes into H2O plus O2 gas. But to balance this, we first need to know how many atoms of each we have. For H, we have 2. For O, we have 2. That's for the reactant side. For the product, we have H is 2, O is 1, plus 2. First, you start with anything but oxygen, leave oxygen to the end. So we start with hydrogen. In the reactants we had 2, in the products we had 2, so it's balanced. Now oxygen, we have O2 and O is 1 and 2. So it's 2 and 3. Most of the time when it's 2 and 3 you have to make it 6. But we do by 3 here, by 2 here and 2 here. Balancing equations is a trial of error. You see trial and error. You see what works and what doesn't. فاحنا here we now have let's try this. So we have 3 times O2, for O is now 6, and 2, so now O is 2 plus 2O2, 4. The O is now both 6, but O is balanced now, and we have to go back and check hydrogen again. Now we have H is equal to 6 and H is equal to 4. So we can see that 322 doesn't work because hydrogen is not balanced anymore. We try another number. If we try H2O2, 2H2O2 and 2 here, you get H is 2, H is 4, O is 4 for the reactant side. For the product side, H is 4, so now H is balanced. O is 2 plus 2. This is your balance formula. 2HO2 liquid reacts to give 2H2O liquid plus O2 gas. A student is asked to calculate the number of moles and atoms in a sample of 17.6 grams of propane, C3H8. To find the number of moles, we use the equation N equals M over M. N is the number of moles. We need to find that. Mass, they gave it to us 17.6 grams of propane. So to find the molar mass of propane, we have to add the atomic masses of all of the atoms. So we have 3 carbon atoms, 12, plus 8 hydrogen atoms, 1. You put it on your calculator. It gives you 44. So n is 17.6 over 44. You put that in the calculator again, you get 0.4, and they want 3 significant figures, so you add 2 zeros and you get 0.4 zeros. To find how many atoms are present in the sample. So to find the number of atoms, you do atoms is equal to n times Na, Avogadro's number, times atomicity. Atoms is n, we already got at 0.4. Avogadro's number, it's given 6.02 times 10 to the power of 23, times atomicity. For C3H8 we have 3 plus 8 atoms for 11, times 11. You can put that into the calculator. 6.02 times 10 to the power of 23 times 11 times 0.4, you get 2.6488 times 10 to the power of 24. Here they wanted to 3 significant figures, so you round it up. 2.65 times 10 to the power of 24. Here they put 2.64, they didn't round it, but they also accept 2.65 times 10 to the power of 24. A sample of O2 gas contains 9.0 times 10 to the power of 21 molecules. How many moles of O2 does this sample contain? So we have what's it called? Equation. It's the number of moles is equal to actually molecules big N is moles N times Avogadro's number Na. So we can rearrange that and get N moles is equal to molecules over Avogadro's number. N is big N, 9.0 times 10 to the power of 21 molecules over Avogadro's number is 6.00 times 10 to the power of 23, and you divide this on your calculator. 9.0 times 10 to the power of 21 over 6.00 times 10 to the power of 23. You get 0.015, and you want it in scientific notation to 2 significant figures. 1.5 times 10 to the power of minus 2. When you move the decimal point to the right hand side, the power of the 10 is negative. 1.5 times 10 to the power of minus 2 moles. How many grams of O2 does this sample contain? So we got the moles of O2, so now you need the grams. We have mass in grams is the number of moles times the molar mass. So we have the number of moles 0.015 times the molar mass. Again, O2 is diatomic, so you use 32 instead of 16. You get 0.48. Again, they put here 0.48, but they wanted a scientific notation in the beginning, so you move it one place to the right hand side. That's 4.8 times 10 to the power of minus 1. Magnesium Mg reacts with oxygen gas O2 to produce magnesium oxide. MgO, and a white bright flame. Calculate the mass of oxygen gas O2 needed to react completely with 4.8 grams of magnesium Mg, producing 8 grams of magnesium oxide MgO. They gave us the chemical equation. It's balanced 2Mg, 2Mg, O2 and 2. Here they gave us the mass of the reactant 4.8 and O2 is X, and they gave us the mass of the product is 8. Using the law of conservation of mass, you can know that mass is always conserved. If we put 4.8 plus X equal 8, X is 8 minus 4.8 and X is 3.2. You don't need to do RGR or anything for this. You use the law of conservation of mass, so you get 3.2 as your answer, and it's already 2 significant figures. Aluminum reacts with oxygen gas to produce aluminum oxide, Al2O3. The chemical equation for the reaction that takes place is 4Al plus 3O2 produces 2Al2O3. A sample of 108 kilograms of aluminum is reacted with excess oxygen gas to produce aluminum oxide. Find the number of moles of aluminum in the given sample. فاحنا we said before, to find the number of moles, you divide the mass by molar mass. Here they give us the mass in kilograms. For this equation to work, you need the mass in grams. To convert from kilograms to grams, you multiply by 1000. We have 108,000 grams of aluminum over the molar mass is 27, and you put it on your calculator, you get 4,000. I have 4,000 moles of you have 4,000 moles of aluminum. Now for the oxygen, you can use RRGR. We check if the equation is balanced. 4Al and 4Al, 6O and 6O. Yeah, it's balanced. We be RRGR. We have 4,000 moles in the RGR and X moles for O2. 4 in the RR for Al and 3 for O. You cross multiply, so 4x is 4,000 times 3, so 4x is 12,000, and x, you get it, 12,000 divided by 4 is 3,000. You get the number of moles of oxygen to be 3,000 moles. Calculate the mass in kilograms of oxygen gas consumed by the reaction. We said before that mass is the moles times molar mass. We have the oxygen, we have 3,000 moles times the molar mass. We said oxygen is diatomic, but we don't use O, we use O2, which is 32, and you get 96,000. Now this is the mass in grams. They want it as they said here, kilograms. You divide by 1,000 and you get 96 kilograms of oxygen. Oh yeah, and they wanted to 4 significant figures, so you put 0.00. As we said before, a mixture of water and ethanol. Water and ethanol, they have close boiling points. Ethanol, I think 78 or 73, and water, we know it's 100. That they have very close boiling points. And we said before, for close boiling points, we use fractional distillation. Fractionating column. They want a fractionating column. You know it from. It's going to be a long tube. On top of the round bottomed flask, it's going to have those dots inside, obstacles, and cooled by air, so it's not gonna have anything in it other than the obstacles. Which of the following is true about the fractionating column? It is used to perform a simple distillation. No, we don't need a fractionating column to use simple distillation. It is an apparatus that we use water to cool vapor and condense them into liquid. We don't use water, we only use air in it, as we said before. It is a long vertical tube containing obstacles and cooled only by air. Yes, we said that before as well. So it's only cooled by air. Key point to remember. Select the picture that represents a technique used to separate the components of a solution of salt and water. فاحنا the first picture we have here is simple distillation. You don't see a fractionating column, and yes, you use that to separate salt and water because they have 4 boiling points. Filtration. Salt dissolves in water, so if you filter it, it will just all fall down. And paper chromatography, you don't use it for salt and water, you use it for complicated substances like ink, for example, that's made of many components. Indicate how the potential energy and the kinetic energy of particles in a liquid change as the system is moved between the indicating points. So we have from point A to B. We have A to B here before the phase change. The temperature goes up. As temperature goes up, temperature Celsius goes up, also absolute temperature goes up, so it's Kelvin. And we know that T is directly proportional to KE, kinetic energy. So as the temperature goes up, kinetic energy increases and potential energy stays the same. While here T, or the temperature, stays the same, so does kinetic energy. So kinetic energy stays the same as well, and potential energy increases. And here it goes up again from C to D. Temperature goes up, kinetic energy goes up, and potential energy stays the same. Nitrogen monoxide gas NO reacts with oxygen gas O2 to produce nitrogen dioxide gas NO2, releasing 56 kilojoules per mole of nitrogen monoxide. فاحنا first we have to balance it. Leave the energy to the end. First we write the basic thing is NO gas reacts with oxygen gas, O2 gas. Now they said gas here, but that's what it's called. To produce nitrogen dioxide gas, NO. Sorry, to produce NO2 gas. Plus 56 releasing. So when they say releasing, you put it in the product side. 56 kilojoules. So we start balancing. as I said before, balancing is trial and error. NO and O2, we start with N. N here is 1, O is 1 and 2, N here is 1, O is 2. We have NO plus O2 gives NO2. As we see here, N is already balanced, O is not, but we have to see what numbers can make O balanced. If we put 2 here and 2 in the product, N becomes 2 in the reactants. In the product, N becomes 2. O becomes 2 plus 2 because the coefficient here, and O becomes 4. So now we can see that it's balanced, and now we have 2 moles of NO instead of 1. And remember, they said here releasing 56 kilojoules per mole of nitrogen monoxide NO per mole. So here we have 2 moles, so you multiply 56 by 2 and you get 112. So the new balanced formula is 2NO gas plus O2 gas produces 2NO2 gas and releases 112 kilojoules of energy. A sample of 4.6 of sodium metal Na is dipped into excess water. An explosive reaction occurs producing an aqueous solution of sodium hydroxide and hydrogen gas. فإحنا here we have to balance the equation again. We have Na, sodium metal, metals are solid, plus H2O. When they say water, it's liquid. A reaction occurs producing an aqueous solution of sodium hydroxide, NaOH, AQ for aqueous, plus H2 gas. For now we balance. As I said before, balancing is trial and error. We try. First we see how many moles of how many atoms of each we have. Na is 1, H is 2, and O is 1. Na is 1, O is 1, H is 1 and 2. We start with sodium Na. It's 1 atom in the reactants, 1 atom in the product, balanced. So it's balanced. H2, H is not balanced. We see how to balance that. If we put 2 here and 2 here, the H's become 4, and H becomes here 2 plus 2. So now H is balanced. We check for Na. Na here is 1, Na here is 2. It's not balanced. But to balance it, we add a 2 here. And now Na and H are balanced. Now we check for O. Now we have 2 O's 2, and here O's 2 as well. But here now it's balanced. And we can see it here, 2Na solid plus 2H2O liquid plus 2NaOH aqueous plus H2 gas. So it's balanced now. Find the number of moles of sodium metal reactants. They gave us 4.6 grams, and we also know that N is M over M. So mass is 4.6 over molar mass is 23. You put it in your calculator, 4.6 over 23. You get 1 over 5 or 0.2. And they set two significant figures, that's 0.20. And for the last one, find the number of moles of hydrogen gas released. We use RRGR. For GR, sodium metal, we have 0.20. That's for the GR. And for the moles of hydrogen released, we have X. And for the RR, it's given 2 and A and 1. If you multiply 0.2 times 1 equals to 2 times X. So 0.2 equals 2X. You divide it by both sides by 2. You get 0.1 equals X. And again, two significant figures for 0.10. A sample of 0.500 moles of butane gas undergoes complete combustion under RTP conditions, according to the following chemical equation. We check if the equation is balanced. 2 times 4 is 8 for carbon, and we have 8 for carbon, and 20 for hydrogen, and 10 times 2, 20 for hydrogen, 13 times 2, 26 for oxygen, and 16 plus 10 for oxygen, but the equation is balanced. Find the number of moles of oxygen gas needed to react completely with 0.500 moles of butane gas. So we have butane gas, C4H10, RR, GR, we have 0.500 moles of butane, and we need oxygen, X. For the RR, 2 for butane and 13 for oxygen. You cross multiply, 13 times 0.5 equals 2X. So 6.5 equals 2X. And you divide 6.5 by 2, or you divide both sides by 2. You get 3.25 equals X. They wanted the 3 significant figures. We have the 3 significant figures, so the answer is 3.25 moles. Find the volume of oxygen gas needed to react completely with 0. At RTP conditions. At RTP, we know that 1 mole takes 24 decimeter cubed. The volume is moles times Vm. Vm is whatever they give you for RTP or STP. So we have the moles 3.25 times 24 because they said RTP. You put it into your calculator, you get V is 78, and they wanted 3 significant figures, so you put 0.0. Air is 20% oxygen gas. Find the volume of air needed for the given sample of butane gas to react completely. In term 1, we took the equation V air is equal to VO2 times 5. because air 20% oxygen gas. We have 78 times 5 for VA. Your calculator, you get 390, and that's your answer to 3 significant figures like they asked. Hydrogen gas combines with oxygen gas to form water. The reaction involves an energy change of 284 kilojoules per mole of hydrogen gas. The energy diagram of the reaction is shown below. Choose the nature of the described reaction. We can see it from the energy diagram that before, the energy in the system itself of 2H2 plus O2 was higher than the product. So energy went down, energy got released, and energy gets released in whenever this thing goes down, energy gets released, and energy gets released in exothermic reactions. When 1 mole of water is produced, 284 kilojoules of energy is released, just like we said. What is the amount of energy involved when 0.50 moles of hydrogen gas are consumed? We write the equation. They gave it to us أصلا, and it's balanced. 2H2 plus O2 gives 2H2O. They want 0.5 and 284 kilojoules per mole of H2. Here we have 2 moles of H2, so we will multiply by 2. You get 568 kilojoules of energy. For RR, we do RRGR. RR for H2 is 2. For kilojoules, it's for energy it's 568. These two, they need to be the same unit. The other one can be another unit, it's okay. For GR we have 0.5 and we have X. You cross multiply. 568 times 0.5 equals 2X. 568 times 0.5 is 284 equals 2X. If I divide both sides by 2, you get 142 equals X. So when 0.5 moles of H2 is put into the reaction, you get 142 kilojoules of energy released. And they wanted 3 significant figures, and it's already 3 significant figures. Zinc reacts with hydrochloric acid and releases hydrogen gas according to the following chemical equation. A student added 0.109 grams of zinc granules to excess hydrochloric acid and collected the hydrogen gas released at RTP conditions using the apparatus shown below. Calculate the number of zinc granules consumed in the reaction. We have number of moles is M over M. Here M is 0.109 over the molar mass 65.4. You put it in your calculator, 0.109 divided by 65.4. You get 1.6 repeated. You get 1.67. I rounded it up to 3 significant figures times 10 to the power of minus 3. On the calculator it shows you 1.666667 continuous on يعني. You round it to how many significant figures that they want. and they want 3 significant figures and scientific notation. 1.67 times 10 to the power of minus 3. Calculate the number of moles of hydrogen gas collected at RTP conditions. They want now a number of moles of hydrogen gas. فاحنا we already got the moles of zinc. For RRGR we do RRGR. For zinc it's we got 1.67 times 10 to the power of minus 3. And we don't know the moles for H2, so we put X. For the RR we have 1 mole of zinc and 1 mole of H2. You cross multiply. So 1 times 1.67 times 10 to the power of minus 3 equals 1x. 1.67 times 10 to the power of minus 3 equals x. Locate the syringe indicating the total volume of hydrogen released at RTP conditions. Note that the volume is measured in centimeters cubed. فاحنا we said we have 1.67 times 10 to the power of minus 3 moles of hydrogen gas. And V gas is equal to N times Vm. Now Vm they gave it to us in RTP is 24. 24 decimeters cubed. So it's N this times 24 you put it in the calculator to make your life easier. You get 0.04008 decimeters cubed. Now they said here that it is in centimeters cubed, not decimeters. So you multiply by 1000. 0.04008 times 1000 you get 40.08. فاحنا the correct answer here. You choose the one for 40. This is 10, but this is wrong. This is 22, so this is wrong. And this is 40, so this is the correct one. And for the last question, iron reacts with chlorine to produce iron tetrachloride according to the following unbalanced chemical equation. But they want us to balance it. They said do not include state symbols in your equation. So we have Fe plus Cl2 equals FeCl3. When it's the same thing, we use 2 and 3, it's always 6. When they give us 2 and 3. But we put 3 here and 2 here. For chlorine, now it's Cl is 6 and Cl is 6 here. Fe is 1 and Fe here is 2. But we need to balance iron. But we put 2 here and now it's balanced. How many moles of chlorine are needed to produce 6 moles of iron tetrachloride? So we do RRGR. They want moles of chlorine and they gave us iron tetrachloride. In the RRGR we want the moles of chlorine, so we put X and 6 moles of iron tetrachloride. For the RR we have 3, they gave us in the balance is 3 and 2 for the iron tetrachloride. 2 you cross multiply. 2x is 6 times 3 2x is 18, and you divide both sides by 2, so x is equal to 9. Two significant figures. X is 9.0 moles of chlorine. So this is chemistry quiz. Yeah.